The cytoskeleton plays an important role in intracellular transport, but its specific functions may seem confusing. Luckily, with the city as our campus, we have one of the largest pieces of infrastructure in the United States, the New York City subway, here to help us explain these cellular functions. Now let me explain. The cell is given its structure through a network of filaments known as the cytoskeleton. It provides structural support, enabling processes such as cell division and phagocytosis. However, our analogy today looks at how the cytoskeleton engages in intracellular cargo transport. The three main components of our cytoskeleton are the microfilaments, microtubules, and intermediate filaments, with microfilaments and microtubules acting as tracks for motor proteins. With these functions in mind, these cytoskeletal tracks are suspiciously similar to the subway tracks we see in our everyday lives. Let's say I wanted to go to my friend Ishar's place for some MCB and chill. I would need to take a form of transit that will quickly and efficiently transport me a relatively short distance across the city. Clearly, the local subway is the option for me. In the cell, actin are akin to these local trains. They move material across short distances based on a set directionality. Oh, and I forgot to mention, both are constantly braking. However, unlike the constant disrepair of New York's infrastructure, actin are broken intentionally in order to maintain a dynamic equilibrium of actin filaments and their building blocks, G-actin. This process is known as actin treadmilling, which involves the assembly of the actin filament preferentially along its plus end and the disassembly of the actin filaments on the minus end. The process is accelerated by the proteins profilin and cofilin, which work as the track's maintenance crew. Profilin helps to promote growth on the plus end, while cofilin promotes disassembly on the minus end. These tracks are then regulated and capped by a series of filament capping proteins, which serve as the final stops to our newly built lines. Now that we have the track built, the cell uses myosin, which act as the subway cars to our subway system. Myosin are responsible for carrying the cargo in the transport system, moving it from the minus end of the actin filament to the newly synthesized plus ends. This sense of directionality is very much akin to the uptown and downtown trains in New York.
Hi, I'm the other guy doing this project. On the other hand, microtubules are similar to that of the commuter train lines, like the NJ Transit or Long Island Railway. In contrast to the smaller actin monomers, microtubules are long rigid structures used for long-term transport. Their length and reliability are similar to the commuter trains of New York, which carry thousands to and from the city every day. They even have their own central terminals in the form of MTOCs, or microtubule organizing centers. These centers are akin to Penn Station at Grand Central Station in that a lot of long-distance trains extend out from these stations. Like the NJ Transit, they carry lots of heavy cargo to and from faraway places using the biological equivalent of high-speed rail, dyneins and kinesins. Like myosin, dyneins and kinesins walk down the microtubule to deliver their cargo away from and towards the MTOCs. Kinesins walk toward the positive end to carry organelles and secretory vesicles, while dyneins moonwalk back towards the MTOC to carry lysosomes, late endosomes, and much more. I don't know about you, but I'm sure those kinesins and dyneins have a better time at the MTOC than I do at Penn Station, though. Microtubules are broken and formed in a different way than actin filaments, with their own form of dynamic instability showcasing their role as more stable long-distance commute trains. The stability of microtubules depends on the presence of GTP beta tubulin caps. If the GTP beta tubulin isn't present, nothing can cap the going plus end of the microtubule, and thus catastrophe occurs. This breaks the microtubule apart and produces GDP beta tubulin. When the GTP beta tubulin is present, the microtubule production is stabilized, and elongation can rapidly occur preferentially along the plus end. This is known as rescue. When they're broken, scientists call this phenomenon a catastrophe. Like our cells, the major train lines require constant maintenance in order to allow for efficient travel. I guess you could say without maintenance, it would lead to a catastrophe. The MAP, or microtubule-associated proteins, modify the microtubules to perform many different things. Some can help speed along catastrophe, while others can stabilize the GTP cap at the growing end of the microtubules. These MAPs are comparable to the workers and conductors of the transit. They stabilize, maintain, and set the size of the train. In all capacities, the cytoskeleton plays an ingenious role in carrying cargo all around the cell, like the New York subway system. Without this system of transport, the city would shut down. Everyone would probably panic. Each person, track, and train must properly perform their tasks in order for the subway to work. Each organelle, filament, and protein must also fill their tasks so the cell can function. Without either of these networks, their respective overall system wouldn't operate, and that is sus.